So we alluded to this in a previous video, but many acids have more than one proton or H plus to donate, and we categorize these as polyprotic type acids, and these are really common. So an example would be like sulfuric acid or H2SO4, which we've talked about previously. And you can often tell they're polyprotic because the way they're written, you can see for H2SO4, the H2 is right up front. The H3PO4, that's a triprotic acid, that's phosphoric acid. And then H2CO3, this is carbonic acid. These are just several examples, but there are thousands, but these are common that we'll deal with probably frequently in this class. So if we look at the example of carbonic acid, we can break up the reaction into two discrete steps because that's actually what would happen. You'd have the original carbonic acid, H2CO3, pop it into water. It's going to liberate or donate one of those H plus ions, and it's going to present this HCO3 minus ion. We call this the bicarbonate ion. And that has its own equilibrium associated with it, which we will call Ka1 in this case, 1 being the first proton that's given away. Now with this bicarbonate ion, this is what we call an amphiprotic species because it can act both as a base if we ran it in the reverse direction of the first reaction, or it can donate that extra proton in this direction. And of course that has its own Ka as well. We'll call this Ka2 because it's the second proton to leave, and that is considerably smaller. So we can look at these and just do a quick relative strength comparison and see that, well, Ka1 is about 4 orders of magnitude larger. 4 orders of magnitude is the same as about 10,000, so it's about 10,000 times more acidic, the H2CO3 molecule, compared with HCO3 minus. And this is always going to be the case, not necessarily the order of magnitude difference, but the first Ka will always be larger than the second, always. That has to be true because you have to want to get rid of the first one more than the second one, sort of by definition. So how would we solve an equilibrium concentration problem when we have a diprotic acid like this? Well, so just like we did in the previous video where we did this for a monoprotic weak acid, we want to find all of the equilibrium species, including pH at equilibrium, but we're given an initial concentration of this diprotic, the H2CO3. So you write it up. These are the things you want to find. What do we know? Well, we can look in a table to find Ka1, Ka2. We always know Kaw. And the other bit that we know here is our initial concentration of the diprotic, which is 0.02 molar. So that's everything we know. We need to proceed using the same sort of approach that we did with the monoprotic system with a couple small changes. So the first thing that we're going to do here, since we've already collected the relevant reactions, I deleted them here, but they were written there just previously, so we already know those. And the next step was to figure out what the strongest thing in the system was. Well, we could have looked at Ka1 and found out that it was about 10,000 times larger than Ka2 and about 10 orders of magnitude greater than Kaw. So really Ka1 is going to be the most reactive thing that we have in the system, and remember Ka1 relates to that first dissociation. So we're talking about H2CO3 here. So we're going to start by considering that system, and we're going to do an ice table with that. So this should be old hat by now. We feel pretty comfortable. 0.02 is what was given to us in the problem. That was the initial concentration of H2CO3. Some amount X is going to dissociate, and so our equilibrium condition is the exact form that we're used to. We know this has an equilibrium expression related to Ka1, so we can write this up, which is our second step here. Looks something like this. So let's go ahead and try to solve for X using an approximation method, which is really just assuming that this X is negligible or 0. So that looks something like this. I kind of skipped a couple steps ahead, but you can pause and make sure that you can see that really if this goes to 0, then the whole thing oops, and I actually made a mistake here. So this is the real number here. So square root of that value gives us X, and X is 9.3 times 10 to the minus 5. So we can check that approximation just by taking the ratio against what our initial concentration was, which was 0.02, and figuring out what the percentage was. That equates to around 0.5%, and we said before that our criteria for this class is usually anything less than 5% is okay, so we're going to call this good and skip the quadratic. So the next step is just to take x and solve for the things that we know in our original ice table. So that were the concentrations of that first Ka1 reaction, and so x is the same as the proton concentration and the HCO3 minus concentration, so I just wrote that up. And then I can subtract x from 0.02 to get my equilibrium H2CO3. And it turns out, because the Ka is so small to begin with, subtracting 9.3 times 10 to the minus 5 from 0.02 turns out to not show up even in the digits that are significant. So it's the same as our initial concentration, at least within those digits that we're keeping. So now that we've taken care of all the species within that first reaction, we can then use the equilibrium expressions for the other two reactions that we know, the Ka2 and Kw, to get all the other species that we want out of this problem, which includes the CO32 minus, the OH minus, and then of course compute the. So we do this by just writing up the first relevant reaction. So for the Ka2 reaction, that's this bicarbonate popping off that second proton, we know it has a Ka2 like this. We know what the equilibrium concentration of HCO3 minus is, so could we figure out what this carbonate concentration is? Yeah, of course, we can just write up the equilibrium expression. It turns out we know Ka2, we know proton concentration, right? We just established that, and we know bicarbonate concentration. We established that as well. So we could rearrange this equation in terms of CO32 minus, plug in the relevant values, and solve for what that concentration should be. So just doing a little algebra here, we have now CO32 minus is equal to these terms, but remember, we just figured out what X was and said that that was equal to H plus and bicarbonate, which makes a big difference here because they're equal to each other. So if they're equal, then it means those things cancel out and our carbonate ion concentration is actually just equal to our Ka. And since we're done with that carbonate species, the last thing we needed to compute was OH minus, which is related to the Kw. So that was the point of step 5 here. We first dealt with this other equilibrium, now we're dealing with the last one, which is the auto dissociation of water. And anytime we know one of these two components, then we know the other simply because they're related by Kw. And so in this case, hydroxide ion concentration is 1.1 times 10 to the minus 10. We can get the pH very easily just by doing negative log of our 9.3 times 10 to the minus 5 up here. And you may say, well, what about this proton here? Because this proton, are we including that in the pH? Because we determined the first proton here to have a concentration of X, which we are saying, well, we just do the negative log of that, and that gives us the pH. But what happens, because now once HCO3 is created, some amount of that's going to break apart to make H+. Is that, should we add those two things together? Well, yeah, technically we should, but will it matter? And we can check that because if we look at this second expression here, we said, well, carbonate ion is equal to 5.6 times 10 to the minus 11, right? So if that is 1-to-1 with the H plus here, then that means H plus coming from this second reaction should also be 5.6 times 10 to the minus 11. And so what we're saying here is the total hydrogen ion concentration in solution is going to be the sum of that coming from this reaction and the first reaction, and technically the reaction of auto dissociation water. But if you add this number, 5.6 times 10 to the minus 11, to the first proton concentration, which is 10 to the minus 5, turns out that that's 6 orders of magnitude difference, and it won't matter. It won't add up in the digits that we're keeping as significant. And so in the end, the pH is simply going to be the negative log of this first proton concentration, which in this case is 4.03, and we're keeping 2 digits past the decimal as that was the constraint in the number of digits that we had significant in this problem.